Let's have sample problem 4.10. We have here uh, 450-pound load hangs from the corner C of a rigid piece of pipe ABCD that has been bent as shown. The pipe is supported by a ball and socket joints A and B, which are fastened respectively to the floor and to the vertical wall, and by the cable attached at the midpoint E of the portion BC of the pipe and at a point G on the wall. So what we are asked here is to determine where G should be located, this point here, if the tension in the cable is to be minimum, and also the corresponding minimum value of the tension. Okay, so what we do here is first analyze the problem. No? We have here a ball and socket connection, so therefore the reactions at point A here are the forces along Z, X, and Y. Okay, and also the same as with D. It has components along X, Y, and Z natin. Okay, but what we want here is just the magnitude of our tension and the location of point G here. So we're only interested with this cable here. So we are not asked to find the reactions at point A and point D. Okay? So what we want here is to eliminate all the unnecessary forces that has no value or have no value. Okay? So instead of using moment about a point, if we try to use moment about a line, we can eliminate the unknown forces or reactions at point B and B. So if we choose to have this axis AD, ayan, as our axis of rotation for the application of our moment about a line, we can eliminate the unknown reactions at point A and point B. So what we're left here are the weights. Its value is about 450 pounds, and our tension here, no? So, ayan, that would be our tension. So applying the summation of forces about a line, so its equation is just, we have uh, summation of moment about line, we have line AD, no? Line AD here, ayan. So that is equal to, so we have only two forces here, that is for the tension and for the weight. So we have for our weight, that is just, yung equation ng moment about the line is just lambda dot product R cross F, no? So that is just summation of lambda dot R cross F. Okay? So we only have weight and tension, so we may write this as uh, lambda. Lambda is just the unit vector of our axis of rotation, this one here. Unit vector lambda. That product of our R cross F of our weight. So our weight is, its R is from point A to C. Point A to C. Okay? Or simply, if by principle of transmissibility, we can transfer this weight here from point C going to this point here. Okay? The static condition of our system will not be changed because the point where we transfer our weight is along its line of action. So therefore, ito siya. Ayan. So therefore, the new R here is from the point here going here. So this would be, that would just be, we have here 12i. 12i. Cross product, our F is just 450, the magnitude, and is directed towards the negative y-axis. We have negative j. So we have here cross product of negative 450 j. Yan. And then we have plus. We're done with our weight. How about the tension? So the tension here, it's lambda would be the same. Lambda. Dot product of R cross F. Its R is from points A to E. Okay, from points A to E. So we have AE, cross product of our vector T. So this one here, they are vectors. That will be equal to 0. Let's try to expand this expression or solve this one. We have here lambda. We have that product of 12 times 450. We have our calculator. 12 times 450. We have 5,400. So we have 5,400. We have I cross J is positive K times negative. We have negative K. Okay. Plus, let's write lambda, that product of AE, vector, cross product of our vector T. Yan, that should equal to 0. How about lambda? So let's try solving for lambda before we proceed with this expression here. So to solve lambda, we have here lambda. Lambda is the unit vector that is along line AD, no? Or that is just equal to vector AD over the magnitude AD. So what is our vector AD? So our vector AD is from points A to D. How do we get from point A to point D? No? So we get from point A to point D by going from 12 units from point A to this point here, horizontal. And then we have X, Y, and then Z. No? X, Y, Z. So we have for the X, we have positive 12I. For the Y, we have positive 12J. And for the Z, we have negative this distance here, that is 6. So we have here negative 6K over the square root of the values here. We have 12 squared plus 12 squared minus 6 squared. So if we simplify that expression here, we have our lambda equal to 2/3 I plus 2/3 J minus 1/3 K. Okay? So yan. Now rewriting this expression here, if we transpose this first term here to the right, we have here lambda, that product of vector AE, cross product of our vector tension, that is equal to, we have negative, and what would be our lambda? Our lambda is just 2/3 I plus 2/3 J minus 1/3 K. Okay, that product of negative 540 K. 540 K. Okay, so we have I dot K 0, J dot K 0, and K dot K is 1. So we only have negative 1/3 K, that product of negative 5,400 K. So that would be positive 1,800 times negative, we have negative 1,800. So, ayan. Now, looking at the left hand side of our equation, we can apply the commutative property for this triple product here. No? Using commutative property, we can arrange our mixed triple product as tension, that product of, or lambda cross AE. Okay? Now, what would be the value of our lambda cross AE? So for our AE, here, we already know lambda. Lambda is this expression here. So we need to know AE. Vector AE is just the vector from point A going to E. So how would we go from A to point E? So that is by climbing up 12 units, and then going to the right positive x-axis of about 6 units or 6 feet. So we have here our AE equal to here, or I we have 6 units, so 6I, and then J we have plus 12J. Ayan. Our lambda here would be this one here. Okay, this expression is our lambda. So the expression lambda cross AE is just equal to this one. We have 2/3 I plus 2/3 J minus 1/3 K cross product of 6I plus 12J. So if we try to solve this expression here, the cross product of lambda and AE is equal to 4I minus 2J plus 4K. Okay? Now, what we're asked here is to find the minimum value of our tension. So looking at here, this expression, we have our T, dot product of this vector here. Okay? This vector. Now, for the dot product, if we want to get the magnitude of this dot product here, what we do is just we get the magnitude of T multiplied by the magnitude of this vector here, lambda cross AE, multiplied by, since we have dot product, we have cosine theta. Okay? And that is equal to 1,800 negative. Okay? Now, this lambda here, this one, is just the unit vector that is along this line here. So, if we don't change point A and point D, this lambda here can never be changed. How about AE? So, AE is from points A and E. So, without changing the dimension of this pipe here, we can never change the value of this AE here. Okay? So, therefore, this expression here is constant. No? If this one here, constant, ayan, our tension here and cosine theta, the whole product of this one, that should equal to negative 1,800. What we want is our tension to be minimum. No? So, take note that if we increase the value, if we know that this part here is constant, and if we want to increase the value of our tension, we need to decrease the value of our cosine theta, no, in order to have the same value on the right hand side, 1,800. No? Inversely, if we want to decrease our tension, we need to increase this one in order na the same pa rin, 1,800. What we want here is for this to be minimum. If you want here for this to be minimum, it should be that our cosine theta here should be maximum. And we know that our cosine theta from the value 0 to 90, we have our cosine theta as 1 to 0. Cosine 90 is 0, cosine 0 is 1. Okay? So therefore, the maximum value of our cosine theta here is when our theta is 0. Okay? Our cosine theta is 0. The maximum value of cosine theta is 1. When will this cosine theta be equal to 1? That is when our theta is 0. Now, what is this theta? This theta here is just the angle in between these two vectors here. So, if we have our theta equal to 0, therefore, the vector T and this vector lambda cross AE, they are parallel. No? Kasi if we have their angle in between theta, that is 0, therefore, this vector T is parallel with this vector lambda cross AE. And if they have, or they are parallel, therefore, their direction cosines, their unit vectors should be the same. No? In this case. So, therefore, whatever the unit vector of this vector here should be equal to the unit vector of this tension here. Okay? So, ayan. So how do we get the unit vector of this vector lambda cross AE? So what we do is we simply divide this one by the magnitude of the vector lambda cross AE. So the unit vector, ayan, if we divide this one here by square root of 4 squared plus 2 squared plus 4 squared, that would be the unit vector that is equal also to the unit vector of t. So that is equal to 2/3 I minus 1/3 j plus 2/3 k. So this would be the unit vector of our t. Now knowing that vector t, again, from this expression here, ayan, our vector t is just equal to the magnitude of t times its unit vector. Okay, unit vector. We already solved the unit vector of t, and that is equal to this one here. So by substitution from this expression here, ayan, our t is just equal to magnitude of t times the lambda. So we have t times our lambda, again this one, 2/3, we have 2/3 I minus 1/3 j plus 2/3 k. Ayan, that product of this vector here, this is equal to this one here. We have 4i minus 2j plus 4k. So we have here 4i minus 2j plus 4k, that is equal to negative 1,800. No? We have negative 1,800. So using that product, we know that I cross j, we have 0, I cross k, 0. So we only have that I dot I, j dot j, and k dot k. So we have here our tension that is equal to 2/3 times 4. I dot I is 1, and then minus 1/3 times negative 2, and then j dot j is 1 plus 2/3 times 4, and then k times k, k dot k is still 1, and then that is equal to negative 1,800. Take note that our t here is the magnitude, okay? So ayan. So solving this one here from our calculator, we have 2/3, 4 minus 1/3 times negative 2 plus 2/3 times 4, that is equal to 6. So we have our 6t equal to negative 1,800. So our t here, that is equal to 1,800 divided by 6 is 300. Okay, we have here, so therefore our answer for letter B, we have 300. Ayan. So for our t here, this would be the magnitude. So we answered the letter B here, the corresponding minimum value of tension. But in letter A, we should know the location of our point G here. Okay? So for the location of our point G, what we do is, here we have only the magnitude, no? So in order to get the vector form of this tension here, what we do is we simply multiply this magnitude by its unit vector. And the unit vector is this one, no? So we have here our vector t, that is equal to 2/3 times 300, we have 200. We have here negative 300. So we have here 2/3 times negative 300, we have negative 200i. Then negative 300 times negative 1/3, we have positive 100j. Then negative 300 times 2/3, we have here negative 200k. So this would be the expression in vector form of our tension. Okay? What we're asked here is to find the location of point G. So this point here. Say that our origin or our coordinate system, its origin is located at point here. This point, this is our y-axis or x-axis and our z-axis here. So if we try to locate this point here, point E, that point is about 6 and the y is 12, and then the z here, the distance from here, from the wall to that point here, that is 6. How about this G here? This point G, we know that along Z, since it's on the plane XY, it has 0 units along Z. So, meron lang tayong X and Y. So, along Y, we don't know. Say, that's X. And yung Y natin, we have Y. And we know that our Z, since it lies on our wall, that is where our XY plane is located, our Z here is 0. Okay? So, ayan. So, since our force, tension, that is equal to negative 200I plus 100J minus 200K is proportional. No? The force is proportional to the length of our cable here. So, taking the proportions, we have our G as our 0.2 and E as our 0.1. We have x2 minus x1. We have x minus 6 over its proportion to our force, which is negative 200. So we have here negative 200. That is equal to, how about y? So we have y2 minus y1. So we have y minus 12 over the proportion of the force along y, we have 100. That is equal to 0 minus 6, z2 minus z1 over its proportion, negative 200. Okay? So using this expression here, we can get x equal to 0, y is equal to 15 feet, and then our z expressed as 0. So in order for our tension to be minimum, our G should be located at points 0, 15, and 0 along x, y, z axis respectively.